This next talk that you're going to hear is part of our major emphasis on supporting young people, early career people. I think you're going to really enjoy it. This is a project we've supported at the University of Michigan, but to introduce it, I am going to introduce our staff member, Ashkan Najad, who has been the project manager of this for the last year. So Ashkan, please go ahead.
Thanks, Greg. Yeah, I'm incredibly proud to introduce the team behind this next presentation. Last year, Survey participated in NASA's XHAB, Exploration Systems and Habitation Academic Innovation Challenge. And the call was to evaluate the viability of mixed reality tools and technologies in the field and how they might also complement existing capabilities. We've had the pleasure of working with a two-group team, the BLISS and CLAWS teams out of the University of Michigan. These are comprised of just exceptional individuals. I'd also like to just take a moment and send some gratitude to members of our Survey teams for lending some of their time and support to this project. So from the BLISS and the CLAWS team, I'd like to go ahead and hand it over to Riley Schnee, Alex Senna, Sahil Farishta, Rupal Nigam, Emily Russell, and Caesar Mu. Guys, go ahead, take it away.
So hello, everybody. Today I'll be introducing the work done as a collaboration between the CLAWS and BLISS teams at the University of Michigan, all to create new tools for future lunar astronauts. CLAWS is the collaborative lab for advancing work in space, which creates human-centered, software-driven applications, all to further humanity's presence in space and streamline mission procedures. Over the last 2 years, this has come in the form of augmented reality or AR software for the Microsoft HoloLens. And BLISS is a bioastronautics and life support systems group. They address the physiological and psychological problems that are needed to improve human space exploration architectures. And this has come over the last 4 years in the form of 6 XHAB challenges with various NASA centers, with our 7th beginning work in September. And I'm Alex Senna. I'm the systems lead for the project this year. The whole team is a multidisciplinary group of undergraduate and graduate students from across the University of Michigan, all developing software to further human space exploration. This current breakdown allows us to start our work from the earliest stakeholder ideations all the way through that final implementation. And this project specifically had the goal of creating that next generation of technology for the unique problems of planetary exploration. Sampling, task management, navigation, and pre-ops planning all need modern solutions before we can comfortably return to the lunar surface. And the collaboration between these two groups formed from the overlapping needs of the suits competition as well as the XHAB challenge this year. The suits RFP specifically mentions granting astronauts new independence while equipping them with new tools specific for the lunar environment. And the XHAB challenge specifically wanted to take these same ideas, but put them in the analog field trek environment to serve as a practical demonstration. And we're not the only team working on this. Several people in industry have been working on AR projects with the same goal. And we've been using Jarvis and HoloSextant as well as many others as inspiration throughout the entire development process.
Hello, everybody. My name is Sahil, and I am the systems administrator for CLAWS. I'll be going over the architecture of our solution. In response to the RFPs, our team decided to focus on making exploratory tasks such as navigation and sampling easier by creating a flexible and non-intrusive toolkit. And we call this system ATLAS, the AR toolkit for lunar astronauts and scientists. ATLAS interfaces with an external server that hosts the CLAWS Mission Control Center. This enables an exchange of information during EVA operations and allows for mission data to either be transmitted to the HoloLens or reviewed later by Mission Control Center operators. To support all of these objectives, we put together mobile support equipment. This includes a suite of external sensors connected to a Raspberry Pi for data storage and processing. To address the drastic changes in lighting in a lunar environment, we have included an external lighting source that is activated by photoresistors. The building blocks of the ATLAS infrastructure are protocols and modules. Each protocol is designed for a specific mission state and has modules which provide the core functionality for each task. In addition, we have some utility classes that contain general use functions to streamline development. The protocol manager runs at startup and ensures smooth transitions and continuity between protocols and their modules. Here we can see an example of the sample collection protocol broken down into the various modules and utility classes that it leverages.
Hello, I'm Rupal, the administrative lead, and I'm going to talk about some of our protocols and modules. For the navigation protocol, our goal is to provide guidance through waypoints while minimizing obstruction to the astronaut's field of view. In addition to the general use case waypoint, we also have special classes for landmarks, sampling sites, and hazards. Astronauts can receive navigational guidance to all types of waypoints, and they can also set waypoints at their current location during an EVA. Here's the data structure of a waypoint. All of this metadata gets captured whenever one is set by either the astronaut or by mission control. For the sampling task, our goal is to support and augment planetary science operations through GeoNotes. GeoNotes are a custom data structure that we created, and they consist of sampling specific mission tasks, associated imagery, audio recordings of voice notes, and the QR codes of the sampling containers. Every GeoNote is also associated with a waypoint, and all of this information is stored on our MCC and can be easily accessed during post-mission analysis. The primary way to interact with Atlas is through voice commands. The naive solution is using keyword recognizer, which maps specified words or phrases to different functions of the backend. However, we can improve upon the solution using conversational AI. Our smart voice assistant is called Vega, which is built using an open source platform and handles natural language processing. We can currently provide information to the astronaut about biometrics and also plan to extend these capabilities to include navigational guidance. On the right, you can see a sample conversation that an astronaut could have with Vega, and as you can see, they can ask about their heart rate, if there are any warnings, and how long the water supply will last.
Hi everyone, I'm Caesar, the Mission Control Center lead, and I'll be giving an overview of our MCC. So the MCC is a web application that relies on a Django web framework and a PostgreSQL database. This serves as a central hub that will be used by everyone on the team in every stage of the mission. So before the mission, the team can come together to review mission procedures and mark any important waypoints and areas on the map. And then next, during the EVA, the supporting team of mission controllers and scientists can enter the control room page. This is where they can see an overview of everything that's happening in real time, including biometrics, communications, and GeoNotes. They can also modify waypoints and mission procedures, such as adding get-ahead tasks, for example. Finally, after the mission is over, the team can go through all the data that's collected and use this information to improve upon the next mission. And then the cycle starts all over again. So here's a look at our navigation tool. We're currently using the Bing Maps API to display all of our waypoints, which you can see in the list on the left. Here's a look at our GeoNotes tool. The notes are listed on the left side, and clicking on a note will pull up the details on the right side panel. Aside from the main mission-specific functionalities, the MCC also provides other miscellaneous tools, such as mock telemetry and warning streams. For example, this is a tool to toggle different warnings that can be used during testing to see how our system reacts to different malfunctions. In terms of the overall design of Atlas, our philosophy is centered around minimalism and uncluttered user interfaces. More importantly, the display needs to be readable in both bright and dark environments. We also wanted to standardize the design across different modules so that the overall system felt clean and intuitive. We kept all of these ideas in mind while creating the mock-ups I see here and on the next few slides.
Hi, my name is Emily, and I'll be walking us through an Adobe XD mockup of our Atlas application. So at the upper left, the task list displays the ongoing mission and can expand to its full length to show previously completed and future tasks. The voice assistant Vega serves as the information center, where astronauts can receive warnings, notifications, and messages. When inputting a voice command, a transcript is shown for confirmation, and the associated action is performed. In the bottom left corner, the minimap displays the astronaut's destination, home base, and no-go zones. The user is fixed in the center and is always facing forward. When they turn, the minimap rotates around them for situational awareness. If an issue occurs with the astronaut's partner, their status will turn red, which can be further expanded to show the associated biometrics. To distinguish the current speaker, a microphone will appear next to their name. Warning messages contain their cause and instructions to resolve the problem. Primary warnings are displayed in red and cannot be dismissed from view. Secondary warnings are displayed in orange and are stored as a small dot above the voice assistant. Astronauts are able to set waypoints at their current location through voice commands. The voice assistant guides the astronaut as they drop and name the waypoint. QR codes are assigned to individual sample containers. When a QR code is scanned, a GeoNote will begin. The voice assistant will display the GeoNote duration, the number of images taken, and a red dot indicating that note taking is in progress. And then once the camera is activated, the window will be wrapped in a green ring indicating the camera field of view. After taking the photo, it'll briefly stay under the voice assistant before disappearing. And then finally, for perspective, this is what our system would look like in the Microsoft HoloLens.
Hi, my name is Riley and I'm the team lead for Claws. I'll be talking about our team's future work. In addition to migrating our Atlas mockups to the HoloLens and conducting testing, we're planning to work on expanding the capabilities of these systems. This includes finalizing control room functionality for the MCC, building external hardware components, and integrating Vega into Atlas. We also have 3 new projects planned for the future. The first of these is RIGEL, which stands for Rock Identification and Geological Evaluation. With this project, we'll handle hazard detection and collaborate more with NASA Survey to develop a Trek API for easier integration with systems such as Atlas. For the second project, we want to create a distributed lunar network of nodes using a peer-to-peer system of small and affordable radio towers, such as the one shown here. This system will be able to support multiple astronauts leveraging the Atlas system and relay information between them. The third project will involve incorporating machine learning into our biometrics module in order to model resource depletion on the fly. This idea originated from a meeting with former astronaut Dr. Jim Bajan, where he suggested that using machine learning in this way could give astronauts in mission control a method for determining if biometrics are following an expected trend. And finally, we would like to thank all of our wonderful supporters. Most importantly, we would like to thank Survey for all of their support and also inviting us to speak today. And that is our presentation. So thank you for listening. If you have any questions or would like to chat, please feel free to reach out to us.
Wonderful. Ashkan, do you have any final thoughts?
I just want to commend these students. These are absolutely one of the most incredible groups of people I've had the privilege of working with, and their self-sufficiency and their professionalism and their commitment has truly been unparalleled. So my hat is literally off to you guys, and I wish you all the best and look forward to continuing to work with you guys.
I agree 100%. And what I've been particularly amazed by is your response. You've continued this work and been very, very innovative despite the pandemic and despite having to work from home, and given some great results. And so anyway, wow, what fantastic work, and thank you for sharing it.
Thank you.